Okay, so in this video, we are going to talk about the Laplace transform. Okay, so let me write the definition. And as we go through this video and the following videos, we'll start to understand more about what the Laplace transform is really doing. So let's start with the definition. So the bilateral Laplace transform. Okay, there's also something called a unilateral Laplace transform. Now I'll explain the difference in 1 second. So we're going to be talking about the bilateral Laplace transform of a signal x of t is the function. Okay, so I'm going to denote it with a capital X, just like for Fourier. We're taking the Laplace transform of little x of t. This is going to be a capital X. And now I'm going to use some math notation to tell you some information. So I'm going to write that x is from c to c. In other words, x is a function whose inputs are complex numbers and the outputs are the complex numbers. So for Fourier transform, the input was a real number, right? That omega, the frequency, was a real number. Here, for Laplace transform, our inputs can be complex, and the outputs can also be complex, just like Fourier. And it's that function defined by what? Well, x of s, so s is our complex number. It's going to be the integral, okay, of x of t times e to the negative st dt. Okay, and this should look pretty familiar because it looks very similar to the Fourier transform. Okay, and we're about to see exactly the relationship. But let me just make a quick note. So as I said, s is a complex number here. Just really want to drive that in. Okay, so this is saying that the inputs to this function x are complex and the outputs are complex. And so we see the inputs s can be complex and the outputs, this function, could also be complex. Okay, so that's a complex number. And now let's look at exactly the difference between Laplace and Fourier, or at least can we create the Fourier transform from the Laplace transform? It turns out we can if we plug in j omega, right? So in the Laplace transform, if I plug in j omega, I get x of t. Just plug that j omega in right there for s, e to the negative j omega t. But wait a second, what was our Fourier transform? X of omega, that was the integral from negative infinity to infinity of x of t, e to the negative j omega t dt. Wow, they're the same. Okay, so i.e., that is, Laplace transform at j omega is the same. It is the Fourier transform at omega. Okay, so if you know the Laplace transform, plug in j omega, and there you go, you get the Fourier transform at that omega value. Okay? But Laplace transform allows us to do more because this s doesn't have to be just j omega, right? S could be, for instance, often we'll denote the real part of s by sigma plus j omega. So now I have this extra variable sigma, okay? So that when I plug it into e to the negative st, I get e to the negative sigma plus j omega t, which is e to the negative sigma t times e to the negative j omega t. Okay, so with the Laplace transform, I have this extra term there, e to the negative sigma t. Okay, and we'll see this more later on. I'm just making a note. I'm going to erase it in a second. But Laplace transform is going to allow us to actually take the transforms of more functions than Fourier. Okay, so let me just erase that now. That was just a quick little note. Okay, well, we'll see many more examples, don't worry. But for now, this is the relationship between Laplace and Fourier. Okay, so what does this bilateral mean? Well, the bilateral refers to this integral from negative infinity to infinity. There's also something called the unilateral transform, which is when this bottom limit is just 0. Okay, but we're going to be looking at the bilateral transform. It's more general. And if we ever want the unilateral transform, we can just throw a unit step function into our x of t, right? If this was like some f of t times u of t, when I integrated this unit step function would zero out the integral from negative infinity to 0. And so we'd be left with the unilateral transform, like just with x of t. And we'll see examples of that as well. But so bilateral is more general, so we'll just look at that. And it turns out this is not the whole story for Laplace transform. There's another part we need to talk about. So it turns out that x of s, the Laplace transform, can exist, i.e. converge. Okay, so this integral can converge for some values of s, but not for others. Okay, so you give me an x of t, and some values of s, when I plug it into this integral, I get a number, I get something that converges. And for other values, it goes to infinity, it blows up, it diverges. Okay. So in other words, there is a region of the complex plane containing all of the values of s for which the Laplace transform converges. Okay, and we're going to be interested in that region, okay, and those values for s that make the Laplace transform converge, and we give that a name. It's so important we give it a name. So here's the next definition. So the region of convergence, okay, which we will almost always denote as ROC. Okay, the region of convergence of a Laplace transform x of s is pretty much what we just said, is the set of all complex numbers where the transform exists. Okay, so in other words, if I want to write it sort of more mathematically, so the ROC is just going to be the set of all complex numbers s such that, okay, that vertical line means such that this Laplace transform exists. Okay, so that's the ROC. And I'll just make a note here that when we take Laplace transforms, okay, we also want to specify the ROC. And as we'll see in a later video, okay, not only do we want to specify the ROC, we actually must specify the ROC, because there can be different functions that have the same Laplace transform. They have the same function of s as their Laplace transform. And so the only way to distinguish them is actually by looking at the ROC. So we'll see examples of that later on in a future video. But yeah, so when we take the Laplace transform, we also want to specify the ROC. Let me just give you an example of an ROC, just so you have something to look at. Okay, so how do we specify the ROC? Well, we can see that it's a subset of the complex plane. Okay, and in the context of Laplace transform, sometimes we call the complex plane the S-plane. And so this real part is really the real part of S, and the imaginary part is the imaginary part of S. Okay, and we have to specify the region containing all of the S values that make some Laplace transform exist. And I'll just draw an example here. Okay, so on this side of this dotted line, maybe the Laplace transform converges. So the ROC would be over here. Okay, so this is the ROC on that side. And on this side, the Laplace transform maybe diverges. Okay, so for those S values to the left of this line, okay, the Laplace transform wouldn't exist because the integral blows up. But for all the S values to the right of that line in the ROC, okay, the Laplace transform converges, region of convergence. Okay, so that's just an example of what it might look like if you had to draw an ROC. And we'll see many more examples as we go on. Okay, so now let me do an example that is trying to sort of highlight the benefit of the Laplace transform, because you might say, well, who cares? You know, we already have the Fourier transform. What does Laplace give us more? And it turns out that we'll be able to transform more functions with Laplace than we can with Fourier. Okay, and kind of a hint at that is that here, if we take a special case of Laplace, we get Fourier. And so you would think Laplace could do more, and it turns out it can. Okay, so to show that, we're going to try to find the Fourier transform of a certain function. And that function is x of t. It's going to be e to the t u of t. Okay, and if you think about what this function looks like, it's 0 when t is negative, and then it's this increasing exponential as t grows. And so based on what we know about Fourier, this function kind of grows too quickly. It's going to blow up when I try and take the Fourier transform. Okay, so that's why I said try, because we're not going to be successful at this, but it's going to be important to see where it breaks down and how Laplace comes to the rescue. Okay, and just so you're not confused, let me just remind you that e to the negative t u of t, a decaying exponential, we actually can take the Fourier transform of that. And since now we're going to be dealing with Laplace and Fourier, when I put this double line or this double arrow, I'll put, if it's not clear from context, I'll put over it whether we're talking about the Fourier transform or Laplace. So that's my Fourier symbol. Okay, so we already saw the Fourier transform e to the negative t u of t is 1 plus j omega. Now we're doing e to the positive t, and we're not going to be successful, but let's try anyway. All right, so the Fourier transform would be this integral e to the t u of t e to the negative j omega t dt. All right, that's our Fourier transform of this function. So now that unit step function, I kind of talked about this earlier with the unilateral Laplace transform. We're doing the same thing here. Okay, the unit step function makes this integrand 0 when t is negative. So I might as well start integrating when t is 0. And I get e to the 1 minus j omega t for the terms that are left. Just combining them. Do this integral, 1 over 1 minus j omega, e to the 1 minus j omega t from 0 to infinity. Okay, so now I have 1 over 1 minus j omega, and now let me plug in. So we're going to get e to the infinity times e to the negative j omega times infinity. Okay, just kind of plugging in infinity for that limit. Minus, of course, e to the 0. But then, let's look at this. We kind of talked about this in the previous video. This part of this number is just going around and around the complex, on the unit circle in the complex plane, and this part's blowing up. So together, this number is spiraling out of control. We saw this before. Okay, so this is kind of going to infinity, just spiraling out of control. And so this Fourier transform actually doesn't converge. Right, that term just blows up. And this one's just 1, so the whole thing just blows up. So this doesn't converge. So the Fourier transform doesn't exist. Okay, so we can't take the Fourier transform of this function. This is just an example. Okay, but now Laplace is going to come to the rescue. Let's find the Laplace transform of, and we're not just going to do that function, we're actually going to make it much more general. That'll be a special case at the end. We're going to look at e to the negative at u of t, where actually a doesn't have to even be real. A is going to be a complex number. Okay, a is an element is an element of the complex numbers. I'll just write that, complex numbers right there. Okay. So once we find this Laplace transform, we'll be able to try and understand what happens when a equals -1. And we'll be able to see from this Laplace transform that we get why the Fourier transform didn't exist, right? Because when a is -1, I get this case that I tried to look at above, and we'll be able to understand better exactly why the Fourier transform didn't exist and what the Laplace transform tells us more, okay? So that's our goal right now. Let's take the Laplace transform of this function. So my symbol for Laplace transform is this kind of script L. Okay, so this is the Laplace transform of x of t, just like Fourier was that, right? So that's Laplace transform. And we're going to denote it capital X with the argument s. Okay. And this is the integral of x of t e to the negative st dt. Now we can plug in for what x is. x is just e to the negative at times the unit step function, e to the negative st dt. Okay, so now this is the integral from 0 to infinity of e to the what? We have negative s plus a t dt, where I plugged in the 0 because the unit step function is 0 when t is negative. Okay, so now what can I do? I can take this integral, so 1 over negative s plus a. We have e to the negative s plus a, I don't need that. E to the negative s plus at from 0 to infinity. Okay, and now let me plug in. Okay, so we're going to get 1 over s plus a, and I'm going to take this negative and just plug in 0 minus what I get when I plug in infinity. Okay, so I'm going to get e to the 0 minus e to the negative s plus a, and I'll just put infinity there. Really, I'm talking about the limit. Okay, and now we have this term here, and this is what the previous video was about. So let me make this note. So we saw in a previous video, I think the previous video, that, okay, what is that limit? That's what we want to look at right now. The limit as t goes to infinity of e to the negative s plus at. Okay, when did we see that this limit was 0? Okay, it was either 0, undefined, or infinity. Of course, we're trying to take a Laplace transform. We don't want undefined or infinity. So our only option left is 0. That's the only one that will work for us in this context. Okay, so when is this limit 0? Well, we saw this, right? Remember e to the zt? When was that limit 0? It was when the real part of z was negative. When the real part of z was negative. That's what we saw in the previous video. So review that if you don't remember. Don't remember why that's the case. So that was 0 if the real part of negative s plus a, the thing multiplying t in the exponent, was negative. That's what we saw. Okay, so this is a fine condition, but we can make it look a little nicer. That's what I'm going to do now. So 0 is greater than the real part of negative s plus a. What manipulations can we do on this? Of course, I can distribute the negative sign. Okay, and then the real part of the sum of two complex numbers is just the sum of their real parts. Okay, you can prove this very easily on your own. Okay, so the real part of negative s minus a is the real part of negative s plus the real part of negative a. And also the real part of negative of a complex number is just negative the real part of that complex number. Again, I encourage you to try proving these on your own. They're very simple. Okay, you can just use the rectangular form of complex numbers to prove this. Okay, and so this is what we get, that 0 has to be greater than this quantity. Well, I can just bring this to the other side. And what do I get? So we need real part of s to be greater than the real part of negative a for convergence. Right? We needed this to be true to get this limit to be 0, so it converged. And we just manipulated that expression and said, okay, we need the real part of s to be greater than the real part of negative a for convergence. Okay, and what happens when we get that? Well, then this would go to 0. That's what we were just talking about. This is 1. And so I end up just with 1 over s plus a. And that is provided what we just found. The real part of s is greater than the real part of negative a. Okay, so that's what we need to get that expression. Otherwise, it diverges. Okay, so let me just write in summary. Okay, e to the negative at u of t, this is what we found, has Laplace transform 1 over s plus a. And we even have found the ROC. We found the region where it converges. Okay, the region where it converges is all of the complex numbers s that satisfy that expression. So the region of convergence is the set of all complex numbers such that the real part of s is greater than the real part of negative a. Okay, so not only did we find the Laplace transform, we also found its region of convergence. That's what we always want to do when we find these transforms. And this whole thing over here, it's sometimes abbreviated. So we abbreviate this as just saying the ROC, and instead of writing all this set notation, everything, we just say the condition usually. Okay, so the real part of S is greater than the real part of negative A. Okay, so let's just see an example of this, of what the ROC might look like for a certain A value. So we have the real part of S, and the imaginary part of S is just the complex plane, sometimes called the complex S plane. And who knows, maybe this was our A value, right? A could be complex. Okay, so maybe this is our A value right there. Okay, and when does this converge? Well, look, we need the real part of S to be greater than the real part of negative A. So where's negative A? Well, to negate a complex number, you negate its real part and you negate its imaginary part, right? Negative, like x plus iy, or sorry, x plus jy is just negative x minus jy. So the real part's negated and the imaginary part's negated. And so all you have to think about is you're just kind of mirroring it through that origin. Okay, so it's going to be somewhere over here, our negative a. And we want to find the region of convergence here, which is when the real part of S is greater than the real part of negative A. Where's the real part of negative A? Well, it's just right here, right? It's right there. That's the real part of negative A going through that dotted line. Okay, the real part of negative A is right there. And we need the real part of S to be greater than that. We need the real part of S to be greater than that. So we have to be on the right side of that dotted line. And that is our ROC. Okay, of course, it goes all the way to infinity. I'm only drawing part of it here because I just have this page. The ROC is everything to the right of that line. Okay, the real part of S is strictly greater than the real part of negative A. Okay, and there's some more vocabulary here. So we call the point negative A, we call that a pole, called a pole, okay, of the Laplace transform 1 over S plus A. And a pole is just, in other words, it's a value of S where the magnitude of the Laplace transform is infinity. Okay, somewhere where the Laplace transform blows up. Okay, that's what a pole is. And so you could see if I plug in S equals negative A, the denominator is 0. And so, yeah, that goes to infinity. Okay, so this is our first example of a Laplace transform. Here's the Laplace transform, and we also found the region of convergence. Both are very important. Okay, and so now we want to try and revisit that question of how could we determine from all of this work with the Laplace transform that the Fourier transform of that function we saw before, e to the t u of t, actually doesn't exist. Let's talk about that right now. This is going to be a really important point. Let me just recall real quick that x of j omega, the Laplace transform at j omega, is the Fourier transform of x of t at omega. So if I'm looking at this complex plane here, where can I obtain all the values of the Fourier transform of x of t if it exists? Well, I just have to plug in j omega. So that's going to be some point on this imaginary axis. Maybe j omega is right there. So when I plug in that value into the Laplace transform, I'm actually getting the Fourier transform for that omega value. Okay, so the thing to take away from this is that if I'm looking at which S values to plug into the Laplace transform to get the Fourier transform, they're all along this imaginary axis. This is where the Fourier transform is occurring in the context of the Laplace transform. Okay, that's what the statement's saying. Okay, so what can we determine from this? This is a really important point. So the Fourier transform exists. Okay, when does the Fourier transform converge? Well, we just said the Fourier transform happens along this imaginary axis. So I would need that imaginary axis to be in the ROC, in the region of convergence for the Laplace transform. So the Fourier transform exists if the j omega axis, i.e. the imaginary axis, right? That's all I mean. The imaginary axis is in the ROC of the Laplace transform. Okay, and that's a really important point. I'm going to star it. Okay, so the Fourier transform exists if the j omega axis is in the region of convergence, right? Because if it is in the region of convergence, then the Laplace transform converges there. But we said the Laplace transform at any point on that j omega axis is the Fourier transform at that value of omega. Okay, so if this axis is in the ROC for the Laplace transform, then the Fourier transform also converges and exists. Okay, so now let's apply this to the example we saw before. So let's consider again the example x of t, which is going to be e to the t u of t. So let's consider that again, so we can try to apply this new understanding. Okay, remember that was the function we tried to find the Fourier transform of, the one that blows up. Okay, let's consider that example again. And how can we use the Laplace transform we just found? Well, as we said before, we want a to be -1, right? If a is -1, then we get the function we're interested in. So a is -1 in e to the negative at times u of t. Okay, that'll give us our function we want. Okay, we'll move this down a little bit. Okay, so the ROC of the Laplace transform of e to the negative at u of t is what? Well, we just found it. It was that the real part of s is greater than the real part of negative a. That's what we just found. Real part of s is greater than the real part of negative a. So what is the real part of negative a for us? Well, a is -1. So this is the real part of 1, which is just 1. So the region of convergence for the Laplace transform of x of t is when the real part of s is greater than 1. So let me draw that. Imaginary part of s, real part of s. So where is a? A is over here at -1. And so negative a is right here at 1. Okay, and our region of convergence is when the real part of s is greater than 1. And so I'm going to draw this dotted line, and I want the real part of s to be greater than 1. So I want to be on this side. This is where the ROC is. Okay, and what can we tell from this diagram? Well, remember, the Fourier transform exists if the j omega axis is in the ROC. But look, it's not. All of these values j omega, are not in the ROC for the Laplace transform. Okay, and so the Laplace transform at any value j omega does not converge. And that means that the Fourier transform of x does not converge, which is what we found. Okay, so let me just write that. So the ROC doesn't contain the j omega axis here. Okay, and so based on our reasoning we just walked through, okay, the Fourier transform of e to the t u of t, which is the function we were just looking at, doesn't exist. And this is what we confirmed. This is what we found before, so this confirms what we found before. Okay, this is what we found before by hand. Going through the process of trying to take this Fourier transform, we found it didn't exist. But here, the Laplace transform tells us more. It not only tells us that the Fourier transform doesn't exist, because this imaginary axis is not in the ROC, but it also tells us which s values we could plug into the Laplace transform to get it to converge. And they're everything out here. You just need the real part of s to be greater than 1, and then you would get convergence. Okay, so pretty cool. So the Laplace transform tells us stuff about the Fourier transform and more, and allows us to transform more functions than we could transform just with the Fourier transform. Okay, so in future videos, we'll be seeing, many more examples. We'll be talking more about what the Laplace transform is doing and more intricacies of it as we go on. Okay, but that's all I had for this video, and I'll see you in the next one.